Welcome to the second part of Module 6. In this lesson, we want to look at those working fluids. So many of the early refrigerants that were used contained chlorofluorocarbons, or CFCs. The problem was they released chlorine when they decomposed, and that goes into the ozone layer and reacts to produce oxygen, which sounds fine except for it breaks down the ozone layer and is a major cause of global warming, so an early contributor to global warming. Now, there are many refrigerants that were developed as a result. So we have refrigerant 11, 12, 13, 22, 502, and 503 are ones that are typically found in most textbooks, okay? But in 1987, they were banned, okay? And they were replaced by hydrofluorocarbons. These don't release chlorine gas. They still contribute to global warming, but not to quite the same degree. These are, however, being phased out and being replaced with just pure hydrocarbons, so no fluorine and no chlorine. The kind of where we are right now historically, the automotive air conditioning systems originally used what was called just Freon, but it was refrigerant 12. And then they moved in the 90s to refrigerant 134A. And this decade, we've been in the process of moving to our 1234YF, which is tetrafluoropropene, or carbon dioxide. And that's a little bit dependent on exactly how the system operates. So there's going to be some minor differences between those two. Most systems, if you buy anything new, it's going to have those. But it's kind of slow to replace things because cars tend to stay on the road for a long time. And so old systems still have some of the old fluorocarbons in them. Refrigerators, such as the one that probably, you got a glass of milk out this morning to pour over your cereal, something like that. Okay, that's typically going to use refrigerant 22 back in the old days. If it's, circa 2000, so 1990s to 2010-ish, it would be refrigerant 410A. And the new ones are using refrigerant 600A, which is isobutane, which has a little issue of it's flammable, or ammonia, which has its little issue also, and it's poisonous. So we have to be very careful whenever these things develop a leak. And so it's, changed the way that people have to design the system. So when we select these things, the number one thing we do try to take care of is make sure that the material is going to be safe or can be handled safely. We also want to think about what it's doing to the environment. Is it going to persist in the atmosphere for a long time? Does it break down? And when it breaks down, what happens to it? Okay. We also are going to have to make sure that that phase change will be possible. The entire system depends on that being able to be evaporated and condensed back and forth at different pressures. So is this phase change possible? If I'm going to have a solid that forms before the liquid, I'm going to be in trouble. Solids don't really move through tubing very well. I also want to think about the pressures. So maybe I can get this phase change for the correct temperatures, but the temperature or the pressure is so high that I have to have really beefy equipment. That costs a lot of money. People would rather not pay that much. And then I have to fill my tubes with this fluid. And how much is that going to cost? And when I do develop a leak and I have to replace it, how much am I going to have to pay for that? And is the material corrosive? Is it going to damage the equipment over time? So let's just look at kind of a potpourri of these various refrigerants. A simple vapor compression refrigeration system that operates between negative 20 degrees C and 40 degrees C. Okay? The evaporator is going to produce just a simple saturated vapor, the condenser a simple saturated liquid. And I want to find the coefficient of performance for a refrigerator using that as a working fluid. Okay, so we've got 6 of these things we're going to consider. Okay, so refrigerant 22, I went through and did the calculations. Again, the spreadsheet is available to you. But what I found out is that the coefficient of performance is about a 3.15. The amount of work I require for the compressor is negative 47 kilojoules per kilogram. That'll get me nearly 150 kilojoules per kilogram for QL, that refrigeration. Okay, so that's refrigerant 22. My pressures I'm operating between 24 megapascals and 153 megapascals. Okay, so let's look at the next one. Refrigerant 410A was the replacement for refrigerant 22. All right, with those same two temperatures, the pressure is now going between 400 kilopascals and 2.4 megapascals. So the pressure's gone up. Okay, I need 51 kilojoules per kilogram of work to get that 150 kilojoules per kilogram of cooling. So a little bit more work. The coefficient of performance is lower, 2.88. Isobutane, or refrigerant 1234YF, okay, has much more modest pressures. So that's a benefit, okay? It operates between 0.07 megapascals. So atmospheric pressure is 101 kilopascals, so 0.1 megapascals. So this is below atmospheric pressure. And the high pressure is going to be 0.53. So this one's going to have to operate under a vacuum. I'm going to get more heat transfer per kilogram, but I'm also going to have, essentially the same ratio of additional work, the coefficient of performance being 3.16 compared to 3.15. So it's not really going to change the coefficient of performance, but it is going to change how much mass is required, and I'm going to have much, much lower pressures. Downside is it's lower enough that I'm going to have to use a vacuum. CO2. Well, now see, this one becomes a problem. Okay? 40 degrees is above the critical temperature for CO2. So I'm just going to go solid to vapor. I'm not ever going to see a liquid. If I don't see that phase change at the conditions of the required refrigeration cycle, I can't use it. Okay? So CO2 will not work as a refrigerant for this system. Ammonia. Okay, so ammonia. Well, 1.5 megapascals, so the high pressure is a little bit about the same as the original R22. The low pressure is nice, okay. It's almost 2 atmospheres pressure. Look at the heat input and the compressor work, okay. My cooling, 1,046 kilojoules per kilogram for compressor work of 319 kilojoules per kilogram. This is a higher coefficient of performance of 3.28, and I'm going to need much smaller quantities of the ammonia to achieve my goal at pressures that are not much different than the original R22. And then water. Once again, my problem here is not at the 40 degrees C like it was for the CO2, it's at the negative 20. That's below the triple point. That means I cannot form the liquid and the vapor. I'm going to, be locked down there where I'm going between solid and gas. So, this is not going to work either. So, for all of these, what would you recommend? Well, I've summarized here all of the various things. I left out the CO2 and water because they don't work. But for each of the various refrigerants and ammonia, here's the coefficient of performance. The highest was ammonia. Okay. For the pressures, I listed all the maximum pressures, and the refrigerant 1234YF, or the isobutane, has the lowest maximum pressure, okay, which means a lower equipment cost. And this over here, the refrigerant 410A, has an incredibly high pressure. That's going to be a very high equipment cost. The R22 and ammonia are about the same as far as that maximum pressure. The minimum pressure, though, so 1234YF looks great for maximum pressure, but for minimum pressure, this is actually a vacuum. So that's a problem. Ammonia is a little bit better than R22 in terms of that lower pressure, and again, they're both better than refrigerant 410A. And the cooling load, kilojoules per kilogram, so the amount of fluid that I would be required to use, ammonia has the lowest amount I would have. So the highest QL, if I have a capital Q, Q equals m dot times little q. So I'm going to have the smallest flow rate required if I choose the one with the biggest specific heat transfer rate. So ammonia is going to be the winner here. Overall, I look at this and say ammonia wins if you can make sure that you can deal with that poison aspect. So we're going to stop here in the last little portion of this video. We're going to look at one last example and see how we deal with reality and refrigeration.